Swayam Prabha. Digital India. Educated India.
Now take a molecular complex, because at the end it is inorganic chemistry. So if we go to an inorganic molecule like this one, a metal in an octahedral coordination geometry, that I have 3 carbonyl groups over there, carbon monoxides, and 3 bromide groups over here. Now the geometry is octahedral, but is the point group or symmetry is octahedral? If you look into it, your answer will be no. This molecule is actually not octahedral symmetry, because for octahedral symmetry, all the ligands has to be same. Now all the ligands are not same. This is which is known as a meridional isomer. And if you try to find out what is the point group, you will find out this molecule also belongs to C2V point group. So here you have that C2 axis. If you rotate 180 degree, this COMBr axial axis, these 3 atoms remain as it is. This bromine goes to 180 degree, this carbon goes to 180 degree, and same and vice versa. So this molecule remains same. So there is a C2. 2 sigma V's are there along with this Br trans and CO plane. So these are the 2 sigma V's. So this molecule is also a C2V molecule. Now the question comes, is this molecule is chirally active or not? Again, what I need to do is actually look into the character table of C2V. And what I typically try to find out whether X and Rx can be activated together. The answer is no. Y and Ry, no. Z and Rz, no. So this molecule cannot be optically active. Okay, so C2V molecule, it is not chiral. It cannot be optically active. Now say I have a molecule, another metal complex. This one, which we have discussed earlier, a bidentate ligand, where NN is nothing but say ethylene diamine. In short form, it is generally written as N. So it is a MN3 complex. And we have discussed earlier this molecule, what is the point group? And you can figure it out. If you look into this particular phase, I have a C3 present over here, and there are 3 C2 perpendicular to it, going through each of this bidentate ligand. So it has a C3, it has 3 C2 perpendicular to C3, and that's why it belongs to a point group of D3. Now, is this molecule is chiral or not? So for that, again, just look into the character table of D3. So this is the character table of D3. Again, these are all available online, so you can just check it later. So now over here, try to find out if X, Rx, and Ry and Rz can be activated together. So over here, you can see X and Y and Rx and Ry have been combined together. So that means they're active in 2 different dimensions. And that is what this term E means. That means it's just doubly degenerate, or it can have 2 different dimensions. So this means this can be activated together. With this E symmetry, you can activate X, Rx, Y, Ry together. Similarly, you can see over here Z and Rz in the same symmetry. A2. So they can be activated together. So in this case, mu E and mu M can be activated together and your molecule can be optically active. Okay, so that is how it is done. And then the most important part is that do I have to find out the point group and look into the character table of each molecule? No, because you already know there are only 2 point groups, 2 sets of point groups possible, which can have XRX, YRY, and ZRZ in the same symmetry. Only 2 sets of point groups. One is the CN, one is the DN. Okay, and N can be starting from 1 to anything. For DN, you have to have at least N equal to 2 because you cannot have a D1 molecule, because you have to have at least N equal to 2 C2 so that you can have other C2s perpendicular to it. With only a C1, you cannot have another C1 perpendicular to it. So that is why in a molecule, this can be N greater than equal to 1. For DN, it has to be greater than equal to 2. Or at any integer value. So these are the only 2 point groups which will be optically active. So from now on, if you want to find out whether a molecule is optically active or not, you don't always need to find out the mirror image and try to match it up, or try to find out SN axis, or try to find out any sigma or I. Just simply find out the point group and see if the point group belongs to CN or DN. If it is, then it is optically active. If not, it's not. And now you know why it is connected, because it has to have this particular property that XRX, YRY, ZRZ has to be activated together so that your mu E and mu M, the dipole moment due to electrical field, dipole moment due to magnetic field, can be activated together so that you can have both this motion happening together so that you can create a helical motion. And once you have the helical motion, you have the property to detect the difference between RCP and LCP. And that is the principal reason that you can differentiate a optical active molecule. Okay, up to here, any questions or query? Please feel free to ask. Don't think that it is going to be a very stupid question or something like that. There's no question is stupid. Every question is good. So if you have any question, please go ahead and ask. Okay, no responses. I assume that everybody is understanding everything. So now we go to the next part. So once we have the understanding the origin of a chirality, now the question is, a chirality we can define or we can monitor in 2 different ways. One is through the optical rotation. And the other one is the ellipticity. Now this optical rotation, we already discussed about that. We call that ORD, optical rotatory distortion, where we actually try to find out what is the change in optical rotation in a range of wavelength. And from there, if you remember correctly, we have discussed about the positive Cotton effect, negative Cotton effect, and plane curve. So the extent of optical rotation varies with respect to the wavelength, and it is very much sensitive to it. On the other hand, ellipticity, we can figure it out by CD or circular dichroism data, which is directly dependent on the optical absorbance, because ellipticity is originated from the difference in the absorbance between the right hand circularly polarized light and left hand circularly polarized light. And over there, what happens that unless and until you have an absorbance in the first place, you cannot have a CD spectra coming. So that is why we are quite sure that where I should look for if it is CD spectra. Although it is also possible that not all the peaks are actually chirally active. We'll come into that in a little bit later. What do I mean by that? Now, you have two options. Either you can run ORD, where you actually find out the change of the optical rotation with respect to lambda, where phi is a function of NL minus NR, or you can have a data of psi versus lambda, where psi is a function of AL minus AR. And the positive and negative is just showing whether it is the value of AL is higher or AR is higher, similar to NL or NR in that ORD. So this is the ORD data. That is how you're going to look into. This is the CD data you're going to look into. Now the question is, which of them is actually will be more reliable data or much more easier data to connect the data with respect to its structure. Now mostly we look into optical rotation so far, but that is actually not the best way to practically monitor an optically active compound, because first of all you have to find out how this phi differentiates with respect to lambda. So how it actually going with respect to that. So something like this, or it's exactly the opposite enantiomer or something like that. So you have to find it out. Now generally when you look into a molecule first, we're probably going to do the optical spectra first. And with optical spectra, we know that wherever you have a maxima, you are going to get a crossing point, a zero crossing point, because of the Cotton effect. And that is why you are going to see a huge change over here with respect to the optical rotation and the wavelength. So that means if you want to pinpoint at which wavelength you should measure your optical rotation, that is very tricky, because even with a very small change, you can have a huge difference. So over here, the change is very sensitive. And you have to first figure it out exactly where it is happening. You have to optimize it. So it is an extra set of experiment you have to do. You have to do it every and each and wavelength and then figure it out. Or you can find out the best possible condition is somewhere where no absorbance is there in a plane curve situation. But in the beginning, you cannot just comment on that because you don't know exactly how it is happening. So that is why if you want to do a ORD data, you have to measure the optical rotation at each and every wavelength, and you don't know at which range you will get the best possible result, because at the condition where it is absorbing, you can have a huge difference, which is very sensitive, and it may happen at a wavelength where there is no absorbance. So you have no heads up call from the molecule or any optical data to exactly where to look into. So that is why ORD data is not that easy to find out. Once you get it, then you can use it. But getting to a ORD data of a new molecule is very much challenging. And secondly, you are looking into a difference between NL and NR, circular birefringence. The change in the refractive index of the left-hand rotatory and right-hand rotatory circularly polarized light. Now, as we know, this refractive index is very much sensitive in a lot of things. What is the temperature? What is the density of the solution? What is the viscosity of the solution? All these different parameters comes and can affect the refractive index. So that means, to imagine if you want to find out a NL and NR difference with respect to ORD, how many different things you have to optimize first. So for an example, over here, I'm doing the same molecule at 1 molar concentration. Somewhere else in other part of the planet, someone is doing at 5 molar concentration. We can end up having different effect on ORD because the density is changing and it is going to have a direct effect on the refractive index changes. So that is why it is also sensitive on the, which is known as the physicochemical conditions. So what do I mean by physical conditions? That means the temperature. That means the pH. If I change the pH, there's a slight change in the overall protein environment around the molecule. It changes the overall arrangement of ionic molecule around it, change the hydrogen bonding environment, that is going to have a direct effect on the NL and NR. So that is why ORD will be dependent on all of them. On the other hand, if you look into the CD spectra is directly dependent on the absorbance. Now the absorbance is also dependent on temperature. If you take the absorbance data at different temperature, you might see some changes. Especially at lower temperature, you will see the absorbance band is much more narrow. At higher temperature, it is much more broad. But to see such extent of difference, you have to change the temperature at a much more larger range. Say from a liquid nitrogen temperature 77 Kelvin to room temperature, then you're probably going to see a very good change. If you're changing it from 298 Kelvin to 315 versus 273, you are not probably going to get a huge difference. So absorbance, although it is temperature dependent, its sensitivity is pretty low. And obviously the CT spectra, we are looking into the difference between AL and AR. If absorbance itself is a property which is less sensitive, the difference of AL and AR will be also less sensitive. So that is why these are much more less sensitive sample. So as we just discussed, a ORD will be very much dependent on the physicochemical condition. Absorbance is not, so the CD spectra is actually going to have a less amount of effect of the physicochemical conditions on the result. Additionally, for a CD spectra, you exactly know what to look into. How? Because first you are going to measure an optical spectra. And from the optical spectra, you exactly know where should you look into, because unless you have optical spectra, you cannot have a CD spectra. So if you take a measurement of the optical spectra of a molecule first, you find there are 4 peaks, only that region you are going to look for the CD spectra. If you are seeing any difference, that means it is chiral. If you're not seeing any difference, it is not chiral, a achiral molecule. As simple as that. So that is why for these 2 important reasons, CD spectroscopy is actually a more reliable and practical experiment that can be used to find out the chirality of a molecule. And that is what is actually used worldwide.